to be on quadrant 2 and quadrant 1, right? And if you have y is equal to negative x squared, you're going to have that on quadrant 3 and quadrant 4. Does that make sense? So it matters where you're going to graph that. Okay, so I can erase this now. So that's for the sign of the leading coefficient. So let's move on to multiplicity versus degree. So you've probably heard what multiplicity is, and also zeros, right? Zeros and multiplicity are related to one another. So for example, you're looking at x, right? So first of all, you have x minus 3, and you have x plus 4, right? So your zeros are going to be 0, right? Because x is a 0. And you have positive 3 and negative 4. So maybe we can just group this based on the smallest versus the largest. So we have negative 4 to begin with because it's x plus 4 is equal to 0. Therefore, you're going to get negative 4, right? And then you have 0, comma 3, right? 0 for your x minus 3 is equal to 3, right? So in that case, you're going to see that the multiplicity of x plus 4 is going to be 1, right? So what is multiplicity? So multiplicity is when you're looking at different terms, and then you call this sort of like an exponent. So if you look at x plus 4, your exponent right here is actually 1, right? So the multiplicity of negative 4 is actually 1. Multiplicity of x minus 3 is also 1, right? So let me erase this so you can see everything. So this is 1, right? This is multiplicity of 1, and this is also multiplicity of 1 because all of your exponents are actually 1. Does that make sense? Okay, so multiplicity is 1, 1, and 1, right? However, if you're looking at the degree of your function, that means the degree is your summation of all your multiplicities, right? It's going to be 3, right? Because 1 plus 1 plus 1 is 3, right? So the degree of your function is 3. Okay, so why does the degree matter? Well, the degree matters because at least you know which quadrant it passes through, right? Because if you're thinking about an odd function versus an even function, right? This is what I tell my students to really remember during the test. So if you're looking at, let's say, a negative leading coefficient, if it's an even function, so say for example, you have negative x squared, right? You would have to, so this is the one that we talked about earlier, you would have to look at quadrant 3 and quadrant 4, right? So you know where your function is going to start and where it's going to finish. So it's going to start at quadrant 3 and then you're going to finish at quadrant 4. So that's the position of where you're going to draw. However, if you're looking at y is equal to negative x cubed, you know that it's not at quadrant 3 and quadrant 4 because it's actually at quadrant 2 and quadrant 4. Does that make sense? So when you draw this graph, you know that if it's degree 3, therefore it's an odd function, right? And if it's an odd function, you're supposed to expect that this is what the quadrants, or this is how your graph is sort of going to look like. So these are what you call like templates that I like to tell my students to remember during the test. So you have an idea of where you're going to start drawing the graph, because otherwise it's just going to be overwhelming. Okay, so now that we have that, we're going to have a number line, and then you're going to graph all of your, sorry, not graph all of your zeros, but plot them, right? So this is negative 4, 0, and 3. Okay, so we know that this is all of your zeros, and then first of all, because it's a negative leading coefficient, it's an odd function, you're supposed to start on top of your x-axis, right? This is your x-axis. And then because you know that the multiplicity of x plus 4 is 1, that means you're going to cross, right? Okay, so here's the thing. If you have an odd exponent or odd multiplicity, you cross. Okay, maybe we can just write that here. So odd multiplicity, that means anytime you have an odd number and it's and it's multiplicity. So say for example, you're looking at 1, 3, 5, 7, right? All of your odd numbers, you're going to cross your x-axis. And if it's an even multiplicity, you're going to bounce, right? So you're only touching, you're not crossing. Okay, so let me just abbreviate that. So cross, and then you're going to bounce, right? So in that case, you're going to cross. You're starting from quadrant 2 because you know it's a leading coefficient of a negative sign. So you're crossing this, right? Again at 0, because its multiplicity is odd, you're going to cross this again, right? And then you're going to cross another one for 3, right? Okay, there we go. So this is how your function is supposed to look like. So you're just crossing, right? But, okay, moving on to part B, right? If your, let's say your exponent or multiplicity in this case is odd, but it's greater than 1, you have what you call an inflection point. So instead of just crossing, so say for example, let's plot this together. So we now have positive leading coefficient. Okay, I'm just gonna abbreviate coefficient as co-f, but that's coefficient. And your zeros are essentially -3, right? X plus 3 and +2, right? And then your degree now is going to be 5, right? And the reason why it's 5 because it's 2 plus 3, right? So degree is the sum of your multiplicity. In that case, because it's an odd function and it's a leading coefficient, you have a template which is y is equal to x cubed, right? And as a result, you're going to have, or you're going to expect that your function is going to start from quadrant 3, right? And then you're going to have somewhere, something on quadrant 1, right? Because it's positive leading coefficient and it's an odd degree. Okay, so we have that written down. Now, how do you draw your graph, right? So when you're drawing your graph, you're going to have -3 and 2, right? Again, we mentioned because it's starting at quadrant 3, that means you're supposed to have your function starting from the bottom, right? So you're starting here and drawing up. So because at -3, you see that it's 3, right? It's an odd multiplicity, however, it's greater than 1. That means you're going to have what you call an inflection point. So an inflection point is also crossing, right? But it's a little bit flatter because you have a change in, there we go. Okay, there we go. So this is flatter as opposed to just crossing because you have a change from concave to convex. Basically, that's what it is. So it's like this right here. So you have a change in your concave to convex, and then this is a little bit flatter, right? So that's what happens at -3. But if you have, let's say, at 2, right? If you're looking at x minus 2 and this is 2, you're just going to bounce, right? And how do you know it's not going this way, right? Going down? Well, if your function is odd, that means you're going to finish at quadrant 1. So that means it has to be on top of your x-axis, right? Or above your x-axis. So you're going to bounce here. Okay, so see that bounce? So it only touches your x is equal to 2 and it doesn't cross that because it's an even multiplicity. Okay, so for even multiplicity, right? For example, if it's greater than 2, what happens to your bounce is it just becomes flatter, right? The greater the number, it just becomes flatter. So for example, this is when multiplicity is 2, right? Versus when multiplicity is 4, right? It just becomes flatter. So this is 4. So when you're graphing, it's just really your intuition that you need to make it flatter. Okay. So I think I've covered everything that you need to know for polynomial functions. And yeah, hopefully this is making sense so far. If you do have any questions, please let me know. Okay, cool. So let's move on to question C. Okay, we can see that this is a rational function, right? So if it's a rational function, that means you're going to have a numerator and a denominator, right? So respectively, you have x minus 1. So if it's a rational function, you need to determine whether it has asymptotes, right? Because we know that rational functions have asymptotes. So we can start with vertical asymptote. So for vertical asymptote, you can really assess that in your denominator. So the whole point of a vertical asymptote is your function does not exist there because you have a break there, right? So at x minus 1, which is x is equal to 1, that's your vertical asymptote. Okay, we do have more space at the bottom. So vertical asymptote is x is equal to 1, right? And how do I know it's x is equal to 1? Well, if it's in your denominator, that's going to be your vertical asymptote. And the reason for that is because if you have, let's say, negative 2 over infinity, right? How do I know this is approaching infinity? Because your vertical asymptote, you don't have your function existing, right? So x is equal to 1, right? And what about your horizontal asymptote? So horizontal asymptote, you're now looking at y, right? But for y, right, you first have to figure out the degree of your numerator versus the degree of your denominator. So horizontal asymptote, again, you have to assess whether your degree of your numerator is less than, equal, or greater than the degree of your denominator. Okay, so here's the following conditions, right, for horizontal asymptotes. If the degree of your, so DEG means degree, if the degree of your numerator is less than the degree of your denominator, so DEN is denominator, that means your horizontal asymptote is 0. Does that make sense? So you don't really have, so in this case, your horizontal asymptote would be 0, right? But, so there's a difference between 0 versus none, by the way. If you say horizontal asymptote is none, that's completely wrong. So you need to make sure if the degree of your numerator is less than the degree of your denominator, it's 0 and not none. Now, moving on to the degree of your numerator, which is greater than the degree of your denominator, and it's only by 1. Okay, so why are we emphasizing that it's only by 1? Well, if it's by 1, that means you're going to assess whether you have a slant asymptote as opposed to horizontal asymptote. So you call this slant or oblique, depending on, again, your teacher, which they prefer, he or she prefers rather. So it's slant